so where we were last time is we were looking at the problem UT plus UX is equal to 0. And I think I started off with, originally I said U of X and 0 equaled e to the minus X. And if I'm on the interval minus infinity, less than X, less than positive infinity, that is not possible. So this would have to be e to the minus X squared. Okay, that's what it has to be. All right, so now if we were to solve this using method of characteristics, we know that our solution is going to be U of X and T. It's going to be e to the minus X naught squared. And we said that X naught was the characteristic of X minus T. So the solution turns out to be U of XT is e to the minus X minus T squared. Okay, so what I was then attempting to do, which I was doing incorrectly, but what I was attempting to do was to solve this problem using Laplace transforms. Okay, so if you do Laplace transforms, when you do the Laplace transform of the equation, you also have to take the Laplace transform of U of X and 0 being e to the minus X squared. All right, so the Laplace transform on the first part of the equation is just going to give me S. So I get the Laplace transform of U sub T. So that's S, capital U of X and S, minus capital U of X and 0. I'm sorry, little u of X and 0, plus capital U of X and S. And that is equal to 0. Okay, so now we end up with U sub X. So this term right here is e to the minus X squared. So therefore I get U sub X plus S, capital U of X and S, turns out to be e to the minus X squared. Okay, so now when I try to solve this, I need that my integration factor mu is e to the integral of P of S, P of, yes. And that just turns out to be e to the S. And this is actually P of, and I don't want to say X, S, I want to say P of X. And that turns out to be e to the, that's what it is. Okay, now we can multiply both sides of this equation. And when we multiply both sides of this equation, we end up getting the derivative with respect to X. Come on now, stop it. we get the derivative with respect to x on this side of e to the sx u of x and s. And on this side, we get e to the minus x squared, e to the sx. Oh, I didn't integrate yet. We just have that. Okay. So therefore, we get, when we integrate this, we now get integral. So this is e to the sx u of xs is equal to the integral of this thing. And that's where the problem came in, okay? The problem came in was that I had e to the minus x. I didn't multiply by this term on the right-hand side. I was able to factor out an x. And then when I factored out an x, it just became a crazy mess. So actually, this is now plus c. And so now I get u of x and s turns out to be whatever this integral is, e to the minus x squared minus sx. And this is x tilde plus a constant. That whole thing is over e to the sx. And then little u of x and t is the Laplace inverse transform of that. Now that's the problem. We can't do anything with that. It is what it is. Okay, so the answer to that first problem is exactly what it is. It's just an ugly integral. Even though we could do it really nice by method of characteristics, this problem, because it is a wave problem, doesn't really work very nicely with the method of characteristics in one variable. Okay, the second problem, which I realized, I thought the second and the first problem had something to do with each other, but they did not. The second problem was not an extension or anything of the first problem. It's its own problem all by itself. And that's where I got confused. Okay, so now let's do the second problem all by itself. So the second problem is a new problem. It's u sub t plus u sub x is equal to 0. U at 0t is equal to 1, and u of x0 is e to the minus x. So now, so unlike the first problem, which was on the interval minus infinity to infinity, this problem is not on the interval minus infinity to infinity. This problem is on the interval 0 to infinity. Which is why it requires a boundary condition. So we have an initial condition and a boundary condition. Completely different problem. Okay, so let's do this problem because this is completely different than the other one. Okay, so now we're going to take the Laplace transform of u sub t plus u sub x is equal to 0. And we're going to take the Laplace transform of u of x and 0 equal to e to the minus x. No, that's the wrong one. Okay, All right, so the Laplace transform of u sub t is going to be S capital U of S and t minus little u of x and 0. And then it's going to be plus capital U sub x of x and s is equal to 0. So now u of x and 0 is the exponential. So that's where that's going to come in. So now I'm going to end up with u sub x of x and s plus capital U of, this is wrong. This should be x and s. Perfect. It's e to the minus x. All right, so that's the first equation. Now the second equation, it says, let's take the Laplace transform of that. So when I take the Laplace transform of that, the Laplace transform of capital U of 0 and t becomes the Laplace transform of u, or capital U of 0 and s. And then I take the Laplace transform of 1, and we know the Laplace transform of 1 is 1 over s. Okay, so this is now a problem for s. So this right here, this whole thing is a ODE in the variable x, where s is the transform variable along for the ride. Okay, so now what I need to do to solve this problem is find my integration factor. It is e to the sx. So I'm going to multiply the left-hand side by that. So I'm going to get total derivative with respect to x of e to the sx times capital U of x and s. And on the right-hand side, I'm going to get e to the minus x times e to the sx. So now on the left-hand side, I get total derivative with, well, actually, let me just simplify it over here. E to the x times s minus 1. Okay, so therefore now I can integrate this. And when I integrate the left-hand side, I just get e to the sx times capital U of x and s. And on the right-hand side, I'm going to pull out a 1 over s minus 1. So s minus 1 is going to pop out. And I'm going to get e to the x times s minus 1. And then I'm going to get plus c. So now c is a constant, but it could be a function of s. Because when you integrate it, remember, s comes along for the ride. So if I differentiated that with respect to s, it could have had with respect to x, it could have had s's in it that would have gone to 0. So now I get u of x and s turns out to be e to the minus x divided by s minus 1. And then I'm going to get plus c, which again could be a function of s, times e to the minus sx. All right, so now I need to use my initial condition. So now I know when x is 0, so u of 0, s, is just 1 over s. So that means that I get 1 over s minus 1 plus c of s has to be 1 over S. So now I know C is 1 over S minus 1 over S minus 1. Okay. So now we put it back together and we get U of X and S. I had e to the minus X divided by, oh, I hate that character, S minus 1 plus bracket 1 over S minus 1 over S minus 1 times e to the minus SX. Okay. All right, so now I need to take the Laplace inverse transform. So we get U of X and T is the Laplace inverse transform of e to the minus X over S minus 1 minus 1 over S e to the minus SX minus 1 over S minus 1 e to the minus SX. Okay, so let's go back to our table. All right, so we have Laplace transform of, so we're looking at this side right here. Okay, so we have S minus 1 to the first power in the denominator, right? So S minus 1 to the first power in the denominator. So let's rewrite this. So Laplace transform of t to the n e to the at comes out to be n factorial divided by S minus a to the n plus 1. Okay. And Laplace transform of e to the at, we know is 1 over S minus 1, or S minus a. Okay. And I think that's all we need. We don't need anything else. Okay, so let's find the inverse Laplace transform of this. So the first term is, I want to find the inverse Laplace transform of 1 over S minus 1 times e to the minus x. Why did I pull the e to the minus x out?
I think it kind of reminds me of the thing that you were doing with the u derivative x.
Exactly. The Laplace transform is on t, so it's an integral of t's. So you can pull the e to the minus x out. Okay? So therefore, this just becomes e to the minus x. And then this just becomes e to the t, because that's the Laplace transform of e to the 1t. And I think I need one more. I think I need, let me see here. I think I need, oh, I don't want to share. Well, I'm sharing. Is there one more that I know? I don't think so. I don't know the inverse Laplace transform, I believe. Oh boy, come back. Of, where am I? I hate that I lost my page. I'm trying to get to A68. Okay. All right, we're at A81. Oh, now we went too far. Oh, no, we didn't. Okay, there it is. Okay, so we only know the inverse Laplace transform when we have a square root. We don't know if we just have e to the as, we don't know it. So that one we're not going to, I don't think we know. Oh yeah, that's what it is. It's a delta function. Okay, so for now, because I want to go on, I'm just going to leave it as it is. Okay, yeah. And we will go back to this. So this part is the familiar part. This is the e to the minus x minus t that we expect to get because of the type of problem that we have. So that's the type of wave that we expect to get. Then the Laplace, we have to use convolution for the other two. So the Laplace inverse transform of capital F of S, G of S, Laplace inverse transform is the convolution of f of t times g of t. And the convolution for Laplace transforms is the integral from 0 to infinity of f of tau g of t minus tau d tau. Okay, so the Laplace inverse transform of 1 over s minus 1 times e to 1 over s times e to the minus sx. So that's two different transforms. So this one is f. And this one is g. So little f of t is the Laplace inverse transform of 1 over s. That's just one. And little g of t is the Laplace inverse transform of e to the minus sx. And have you at all learned delta functions?
I feel like I've heard of it, but I don't really remember it.
You don't really remember it. Okay. All right. Yeah, that is the delta function of, so that becomes the delta function of t minus x. Okay. And I'll take delta function of t minus x. Let me make sure, delta of t minus t naught. Yeah. Okay. So what the delta function is the delta function is infinity at that point and 0 everywhere else. It's infinity, it's like a pulse when t is equal to x, and it's pretty much 0 everywhere else. Okay? So therefore, this is a, so that's the convolution. So for this piece, it's just a convolution of that f with that g. And then for the other piece, for Laplace inverse transform of 1 over s minus 1, e to the minus sx. Then if I let, again, this now be f and this be g. Actually, let's not call it f. Let's call it h. This is a totally different function. So here, h of t, Laplace inverse transform of 1 over s minus 1, and that's e to the t, and then g of t is still the same. Okay. All right. Let me go on to a heat equation problem. So you get u sub t is equal to uxx minus, 0 less than x less than infinity, t greater than 0. U of x and t, u of 0 and t is equal to 70, and u of x and 0 is 0. Okay. So therefore, take the Laplace transform of the whole thing. Equaling uxx. And then the Laplace transform of 0 and t, u of 0 and t, equal to 70. Okay, so your first equation is going to give you s, capital U of x and s, plus little u of 0 and t. Nope, u of x and 0. Plus, now, this is going to give me uxx is equal to 0. So now I'm going to have uxx minus s, capital U of x and s. It's going to equal minus u of x and 0. And that should be, oh, and this should be a negative. So I'm gonna do something, I don't have, this should be positive 70. I'm like, it should not be negative 70. Okay, so now this is a very simple ODE. We have, wait a minute. I feel like I did something wrong. U of x and 0 is 0. Now it's simple. So we get u of x and s is equal to A of S, E to the square root of S times X plus B of S, possibly E to the negative square root of S times X. Now, S we know is positive. We already said whenever we're doing a Laplace transform, S is positive, and X goes to infinity. So here's where our second boundary condition comes in, the hidden one. So there's a hidden boundary condition or a bounded condition as X goes to infinity that says that A of S has to be identically 0. It just can't be there. So now I get U of X and S is B of S, E to the minus square root of S times X. But U of 0 and S is from this equation. It's 70. So that implies that B of S is 70. So therefore U of X and S is equal to, oh, I apologize. That is 70 over S. When I do the transform, when I do the Laplace transform of 70, that's Laplace transform of 70 is 70 times the Laplace transform of 1. So that is 70 over S. Forgot my S. Very easy to forget. So therefore this is 70 over S, E to the minus square root of S times X. Okay. Now, this doesn't look real well, but this is what it is. So I'm going to take you to here. And because I have the textbook, the actual textbook, it's much clearer for me than it is for you. So let me see what my textbook, because that looks like, where am I on page A72? Okay. Yes, E to the minus A square root of S. Okay, that is exactly what it is. Okay, so E to the minus A square root of S. Okay. So therefore, we can see that. I'm going to write it for you. So let's note to ourselves the Laplace transform of, and this is A over two times pi, no, 2 times the square root of pi. T to the 3/2 power e to the minus a squared over 4t is equal to e to the minus a times the square root of s. Okay. All right. Yeah. Yeah. Like I'm going to remember that every single time I get to one of these problems. So u of x and t is, I'm going to pull the 70 out and do the Laplace inverse transform of 1 over s times e to the minus square root of sx. So now I'm going to let this be f. I'm going to let this be g. So f of s is 1 over s. So that means f of t is 1. Okay. G of s is e to the minus square root of s times x, which means little g of t. So here, a is x. So that means g of t then becomes x over two square root of pi t to the 3/2 power e to the minus x squared over 4t. All righty. So therefore, u of x and t is equal to convolution of f with g. So that is the integral from 0 to infinity. I'm going to write this as f of t minus tau, g of tau, d tau. Why? Because f of tau can be 1, and g, you're going to get the same answer regardless how you do it. So therefore, this is the integral from 0 to infinity. Let f of tau be 1. So I'm going to get x over 2 the square root of pi, t to the 3/2 e to the minus x squared over 4t dt. D tau, 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 tau. These need to be taus. It doesn't matter. They could be taus. Still integrates out. Okay, not cute, but that's what it is. All right, is there one that we can find that's some semi-cute? Okay, let's look at this next one. It's a little better. I'm not sure what number this is for today. That really was number 2. Okay, so this is number 4. Here's a this is a wave equation problem. Let me see what else do I have. Do I have something nicer than this? And this example here. That one's a heavy side function. That's not too bad. Ooh. I'm trying to see if I can find anything that's reasonably nice. Oh, here's one. It requires a lot of work, but it's actually not too bad. Okay, this one's not bad. This one is another another heat equation, but it actually has a nice solution. Okay. So this one is U sub t equal to uxx on the interval 0 less than x less than 2. T is greater than 0. So this is one that we could solve using separation of variables. U of 0t equaling U of 2t equals 0, and U of x and 0 is 3 times the sine of 2 pi x. Okay. So if we were to solve this thing using separation of variables, what would we get? Well, we start off with U. So if we did separation of variables, you would get x t prime is equal to x double prime t. So we would divide by xt, divide by xt. So we would get t prime over t is equal to x double prime over x. And we'd set that equal to minus lambda. So then we would get t, x double prime plus lambda x is equal to 0, with x at 0 equal to x at 2 equal to 0. So we already know that this is going to give us xn of x is going to be some bn, the sine of n pi over L times x. And our L is 2. So this is going to be bn times the sine of n pi over 2x. You with me?
Yes.
Okay, good. All right. Then we're going to get Tn t prime plus lambda t is going to equal 0. So if t prime plus lambda t is equal to 0, that's going to give me that t is some Cn e to the minus lambda t. So in this case, we're going to get t n of t is some Cn e to the minus n pi over 2 squared t. Again, n is equal to 1, 2, 3, dot, dot, dot. And lambda n is n pi over 2 squared. So u of xt, I'm skipping a bunch of steps because we've done this so many times. The sum n is equal to 1 to infinity of a n e to the minus n pi over 2 squared t times the sine of n pi over 2x. Okay. So therefore, we get u of x and 0 is equal to the sine of 2 pi and that is equal to the sum n equals 1 to infinity of a n the sine. Oh, did I miss a number? I feel like there was a 3 or somewhere in this problem. There's a 3 there. Yeah, like I said, I feel like there was a 3 there. Okay. Sine of 2n, to 2n pi, so this is n pi over 2x. All right, so therefore, an is going to be 2 over L, which is just 1. The integral from 0 to L of the sine up 3 of 2 pi x times the sine of n pi over 2x dx. And I think the only thing we're going to get is when n is 4. That's my guess. We only get a solution when n is 4 because of orthogonality, but let's find out for sure. So let's go to our integral calculator. And on the integral calculator, we have the sine of 2 times pi times x times the sine of n times pi over 2 times x. That's right. And it's evaluated from 0 to 2. Where's my answer? Aha! And just as I thought, notice that it is 0 except when n is 4. Okay? So it's 0 when n is 4. So that's what I expected. 0 except when n is 4. So this is going to be 3 times just 1 when n is equal to 4 and 0 otherwise. So therefore our answer is that u of x and t is 3. We gotta let n be 4. So n is 4, so that's 3 to the 2 pi squared t times the sine of 2 pi x. Okay, so that was separation of variables. All right, let's do Laplace transform. Okay, so let me rewrite the problem. I had u sub t is equal to uxx on 0 less than x less than 2 T is positive. So again, Laplace transform works when any problem where T is positive. Okay, T is greater than 0. So it doesn't work on everyone, but it works on the ones that satisfy the conditions of the Laplace transform. U of, nope, that's wrong. Nope, that's right. U of 2nt is equal to 0, and U of x and 0 is 3 times the sine of 2 pi x. Okay, this is actually fun doing this Laplace transform, this problem. Okay, so the first thing is going to give me, when I take the Laplace transform, I'm going to get S, capital U of x and s, minus x of x. And then I'm going to get equals capital U x x of x and s. Okay, so I'm going to rearrange this to be U sub xx minus s, U of x and s, to equal positive U of x and 0. Actually, it's negative. So this is minus 3 the sine of 2 pi x. Okay, so this is my problem. It does not look like it wrote what I wanted it to write. Okay, all right. And this particular problem has boundary conditions. All right. So we have to figure out what the boundary conditions are. So the boundary conditions are the transforms of what we have above. So therefore, when we take the Laplace transform, we're going to get capital U of 0 and s is capital U of 2 and s. And that's going to equal 0. Okay, so now this problem is a problem that we need to solve, and it has a homogeneous part and it has a particular part. All right, so U of x and s has a homogeneous part and it has a particular part. Now the homogeneous part is rather easy. Okay, so to get U homogeneous of x and s, I just have to solve uxx minus s u is equal to 0. And we did this before. So U homogeneous of x and s turns out to be A of s times e to the square root of sx plus b of s times e to the minus square root of s times x. And we're on a bounded interval, so we don't have to throw anything away. Okay, we don't have to throw anything away right now. Okay, so now we need to solve for the particular solution. So to get U particular, we assume U particular is equal to some form of this solution. So U particular is equal to some C times the cosine of 2 pi x plus some D times the sine of 2 pi x. Now, we can work this out, but I don't know if you remember from before, because the function and its second derivative of the same, we kind of already know that c is not going to, the c is going to be 0. But let's find u particular prime. So that turns out to be, take out the 2 pi. And I'm going to get minus c, the sine of 2 pi x, plus d, the cosine 2 pi x. And then u particular double prime is going to equal 4 pi squared times minus c, the cosine of 2 pi x, minus d, the sine of 2 pi x. So let's put it into the equation. So I have u particular double prime that's going to give me 4 pi squared minus c, the cosine of 2 pi x, minus d, the sine of 2 pi x. And then I have, gotta remember, I think it's minus s. Yes, minus s minus s times c cosine 2 pi x plus d sine of 2 pi x. And that has to equal -3, the sine of 2 pi x. So when you put it all together, you get negative s, so minus s, plus 2 pi plus 4 pi squared times a has to equal 0. And then you get minus s plus 4 pi squared times b has to equal -3. All right, so a is 0. And b is 3 over s minus 4 pi squared. Okay, so now we get u of x and s is a of s times e to the square root of s plus b of s. Oh, this is a d. I'm sorry. This is a d, not a b. And this is a c. Okay. This is c is equal to 0, and this is d. So this is, yeah, so this is e to the minus square root of s plus d is 3 over s minus 4 pi squared times the sine of 2 pi x. Okay. So now let's apply the boundary conditions. That u of 0 and s equal to u of 2 and s equal to 0. And when you apply those and do the algebra, you just get a and b turn out to be 0. Okay. It's actually not hard to show. you get A, and we're letting e to the s, e to the square root of s, plus b, e to the minus square root of s. I feel like I'm missing an x in here. I am missing, yep, I am. I'm missing an x. Okay. So when you let s be 0, when you let x be 0, you get 0. So you get a of s plus b of s is equal to 0. And when you let x equal to 2, you get a of s e to the square root of, nope, e to the 2 square root of s plus b e to the minus square root of s, minus 2 square root of s. And that has to equal the sine of 4 pi, and that's 0. And so that's why these two things, that's why these two things, look now here, you're getting on my nerves. That's why, let's try it again. Yay, these two things give you a equals b equals 0. Okay, so therefore u of x and s turns out to be 3 divided by s minus 4 pi squared times the sine of 2 pi x. And let's take the Laplace inverse transform of that. So u of x and t is the Laplace inverse transform of 3 over s minus 4 pi squared times the sine of 2 pi x. Now, everything that's x, throw it out. So I'm going to take out the 3, the sine of 2 pi x. So now I'm taking the Laplace inverse transform of 1 over s minus 4 pi squared. I feel like there's a plus somewhere. There's a plus. I lost the plus. Yep, there it is. Right there, I lost it. When I went from here to here, this is a plus. And this is a plus. As soon as I started writing out my answer, I knew this was okay. This is a plus, and this is a plus. This is a plus. And now we know the Laplace transform of e to the at is 1 over s minus a. So the Laplace inverse transform of 1 over s minus a is e inverse, is e to the at, and here a is minus 4 pi squared. So therefore we get u of x and t turns out to be 3 the sine of 2 pi x times e to the minus 4 pi squared t. And that looks like the answer by separation of variables. Nice to end on a very positive note. Yay, see where everything is going and how beautiful it can be and not have something hideous. I will do probably 2 more problems on Monday, and Monday we'll talk about final and all that kind of stuff.
Okay.
All right.